Okay. So let's get to labeling this little picture here. Okay? And we're going to label this in a very kind of general setting. Okay? So you'll notice here we already have some very kind of generic labels on my diagram. For example, I have the point right here, and we call this point C. Okay? So there's no actual X. I'm not going to say it's like 1 or 2 or 3. We're just going to use like a generic number, C. Okay? And then that takes us to this point on my graph of F, right? And then the y-coordinate then would have to be F of C, right? If you plug C into F, well, the y-coordinate gives you is F of C. Okay? So that means this point has coordinates C, comma, F of C. Right? So, you'll see this other point over here. All right, but it does not have an x-coordinate given to it. And that's because we're going to define this x-coordinate not by a separate number. So I'm not going to say like this is D and this is F of D. We're not going to do that, okay? Instead we're going to do it in a very specific way. What we're going to do is we're going to go out a certain distance, x, from that C. Okay, we're going to go out a distance x. And, you know, that distance, well, it's going to be a small change in x, so we'll call that delta X. Uh-oh. Right? People are like panicking now. Their blood's starting to sweat now. It's like, wait a minute, delta X is... I'm starting to think this is starting to be calculus now. All right, so anyway. So if we're going out a distance of delta X, how can I represent this X coordinate? What would that be? C plus delta X. C plus delta X. Okay, and I'll explain why we're setting up in this way in a second, okay? But for right now, we're going to take C, we're going to go out a distance of delta X, and then this x-coordinate becomes C plus delta X. Now, if my x-coordinate here is C plus delta X, what does that mean the y-coordinate here is going to be? F of C plus delta X. Uh-oh, this is starting to be very uncomfortable for us, right? So that means the coordinates then for this point, well, what's the x-coordinate for this point? C plus delta X. Comma, and what's the y-coordinate? F of C plus delta X. Okay. So that all makes sense. No big deal. And again, our goal here is to come up with an we want to find the slope of the secant line. I'm going to go ahead and draw in this secant line that we're talking about. So there's our secant line. So yeah, sorry. If you want, there's a bunch of protractors up front there. If you want to do a nice straight line, okay.
Hey, boy.
Right? No. They think they're ninjas or something. I think it's like Friday and the T-shirts. That's what does it.
I just think kids today are just not in the mood.
Probably.
In my first
just not in the mood.
Jarvis was playing music like loudly out of a speaker.
Yeah.
For like 10 minutes of class.
So there's our secant line. To get that drawn in. Okay, and so let's go ahead and find the slope of that. So let's see, the slope formula, if we remember correctly, is, what's the slope formula? Yeah, y2 minus y1 over x2 minus x1. Okay, so that's like from Algebra 1, right? But now we're going to plug in our coordinates. Well, here are the coordinates for our 2 points, right? These 2 points not only are on our curve, but they're also points on the secant line, right? Like, that's how we made that secant line. We drew it through those 2 points. So, let's go ahead and plug those coordinates in, messy as they may be. All right, so let's see here. So my second y-coordinate is this f of c plus delta x. Minus my first y-coordinate, f of c, all over. Okay? And what's my second x-coordinate? C plus delta x minus my first x-coordinate, C. Okay. Now, believe it or not, right, yeah, there is some simplification we can do here, right? The numerator's got to stay the same. Numerator is still f of c plus delta x minus f of c.
We can look at that for different sources.
But the denominator, what happens? The c's cancel, right? C minus c is left with just delta
Oh my
x.
gosh, it is a difference quotient.
It's a difference quotient. What? So yeah, this is also known as the difference quotient. Okay? So, prior to this, when we've seen this, it kind of didn't have as much meaning to us, right? It kind of was just like, all right, this is a thing that Ms. Widmeyer and my other math teachers have said is important, and we're just going to do it, and we're not really sure why, but he keeps telling me to do this thing, and he's going to keep giving me questions like this on the test, so if I want to do well, I better learn how to do it, okay? Well, now you have some context. What is this thing? This is the slope formula for a secant line, okay? That's what these symbols kind of mean, okay? It's a slope formula for a secant line.
So when we're doing this, do we have to we don't have to write it out as c plus delta x minus c. We can just write delta x.
Right. This is just for this particular situation, since we start with c as our coordinate. Yes. Now, one other thing I want to point out here, the secant line, okay, remember it is not the same thing as the tangent line, right? The secant line, this finds us, this is what we call like the average slope. Okay, or we also sometimes call this the average rate of change. We call it an average because it's the slope between 2 points, right? It's kind of like for this interval, the average rate of change is going to be the slope of this line, okay, or the average slope. It is not what we really want to find, right? What do we really want to find? The slope of a tangent line. But a tangent line only ever intersects our graph at 1 point. The secant line is intersecting at 2 points. So it's not quite what we want, okay? This is the average rate of change or the average slope of our function, okay? What we want to get to is the instantaneous rate of change, right? The instantaneous rate of change, which is the slope at a single point. But how can we get a slope of a line if we only have 1 point? Well, we'll think about that in a second here, okay? So let's move on down here, and there's the question that I just asked. What if we wanted to find the slope of the line at a single point instead of 2, right? Here, 2, no problem. We have the slope formula, but how can we get the slope with only 1 point, right? We can't use our slope formula like that. So let's go to this. All right, so the first thing I'm going to have us do is we're going to find the slope from the point 1, 1. So let's see. I don't know if it's got the... Oh, well, okay, sorry. The point 1, f of 1, and so there's the curve right there. So we're going to find the slope from here, and then from the negative 1, let's see, negative f of 1. So it's going to be like we're going to find the slope from this point to that point right there first. Okay, I'm just like freehand drawing that there, okay? Between those 2 points. Because again, this curve is f. Okay, and this one has coordinates, coordinates negative 1 comma f of negative 1. Right there. And then this is the coordinates, 1 comma f of 1. So we're going to find the slope between those 2 points. Well, it's pretty clear what that slope's going to be, but I mean, what is the slope? It's going to be 0, right? Okay, and we can try this one down here. So again, this has a point of 0 comma f of 0, right? So let's see here. Maybe we'll actually do the math this one. So f of 1, according to my graph, what is f of 1? 2. Hang on. And then what is f of 0? 3. And then 1 minus 0, because it's the 1 minus the 0 there. So we get negative 1 over 1, which is just negative 1 then. So, sorry, question, Brittany? You good? Yeah, Brandon?
0, f of 0. That point.
This point right here? Okay, so 0 is the x-coordinate, and then f of 0, which is 3, is the y-coordinate, okay? Because, right, we're normally used to writing just the y-coordinate, but here I'm writing just f of 0. Okay? So there's that. So okay, so we go from slope of 0, to now when I get closer there, it's a slope of kind of negative 1. I didn't do a great job drawing that. I should probably go down like through that instead. So ignore that part. Okay, but now we want to find f of 1 minus f of 1 over 1 minus 1. Well, f of 1 is what?
F1 is 2.
2, and then f of 1 is 2 over 1 minus 1. We get 0 over 0. So, yeah. But if we look at this point, does it seem like we should get a value here? In fact, what do we want to say our slope is going to be? Negative something, right? It's going to be a negative slope at least because it's going down as we go from left to right there. But again, how can we find the slope when we can't, do the slope at a single point like that? So what can we do? So flip over here, okay, and we're going to relabel everything we just saw. So, okay, so all right, you got this guy with the delta x. This is c plus delta x. This is c f of c. This is c plus delta x, comma, f of c plus delta x. And this is f of c plus delta x. I'm going to draw in my secant line again. Okay. So just relabel everything there. And so the purpose of what we did on the front, was I was trying to show you that we kept this point. We kept this point, but what did we do to this other point? The other point we kind of like brought in closer, right? We started at -1, then we brought it in a little bit closer to 0, then we brought it in a little bit closer, to the exact point, but we could no longer do it. All right? So here we're going to try and follow the same principle in general, right? We have this point C, and we want to try and bring this point in. The closer we bring this point in, the more this secant line is going to start. As I bring this point in, the more that secant line is going to start to approximate my tangent line. Okay? How can I reduce the distance between these 2 points? What is that? What concept that we just talked about last unit? A limit. Okay? And so what do we want? We want the limit as what? What do we want to shrink? How can we shrink this? Well, we want delta x to get small. So what do we want delta x to approach then? We want delta x to approach not c. Remember, delta x is a distance. So we want to shrink this distance. We want it to approach 0. And so we want to take the limit as delta x approaches 0 of our slope formula, which is f of c plus delta x minus f of c all over delta x. And that will create a tangent slope. Okay? You hate limits. But that's it. That's how we create a tangent slope. That's how we're going to find a tangent slope. We're going to take the limit as delta x approaches 0 of our secant slope. And as we do that, this point will stay fixed. This point here will stay fixed. This point will move in closer and closer and closer because delta x is shrinking. And as it gets closer, this secant line is going to get closer and closer to approximating and then essentially becoming our tangent line. So as delta x gets smaller, that is, in parentheses here, approaches 0. Okay. The second point gets closer to the first point. Okay? As a result, the slope of the secant line, so again, as delta x gets smaller, that is approaches 0, the second point gets closer to the first point. As a result, the slope of the secant line gets closer and closer, okay, to the slope of the tangent line. In fact, it approaches the slope of the tangent line. And so that is why I've been having you guys practice that for so long. Okay? That's why all your calculus teachers and your pre-calculus teacher maybe has had you practice this, because this thing solves the tangent line problem. This is a solution right there. You start with a secant line, you shrink the distance between the 2 points by bringing in this point, we approach that tangent line. Okay, yeah, Brandon.
Is that why we always get things like in slope-intercept form, like 2x plus 6 or something like that? Right?
So-
In that sort of form, not
You-
exact.
So that we'll get into that a little bit here later. You'll see kind of like what's going on. So sometimes they're in slope-intercept form, sometimes they're not, and so it's not quite the meaning. Remember, all we're doing when we do this is finding the slope. That's it. So the y-intercept is going to be a different kind of thing that we do.
That's the slope.
It's like a formula for the slope, is what I want to say.
If you get 2x plus 6, that would be like 2x plus 6 x
That's-
plus b.
So yes, exactly. And the 2x plus 6, it will give you the slope at any particular point, right? So for example here, the slope is changing for different x values, right? For the x value here, my slope is going to be different than the x value here. So you will give the x value, and you're like, okay, let's say I want to find the slope at x equals 3. You plug 3 into 2x plus 6. 3 times 2 is 6, plus 6 is 12. So the slope is 12 at x equals 3. But at x equals 2, 2 times 2 is 4, plus 6 is 10. The slope at x equals 2 is 10. You see what I'm saying there? So it's a slope formula for the slope. Anyway, so the definition of the tangent line with slope m. If f is defined on an open interval containing c. So f is defined on an open interval containing point c, and if the limit exists, then the line passes through the point c f of c. The line passing through the point c f of c with slope m is the tangent line to the graph of f at the point c f of c. Okay? The slope of the tangent line to the graph of f at the point c f of c is also called the slope of the graph of f at x equals c. So these are interchangeable, synonymous words. Okay, that's one thing we really want to keep our toes on, or make sure we have on lockdown in our brains. Is there's multiple ways in calculus to ask the same question. So if you're asked to find the slope of the tangent line of f, that means the same thing as finding the slope of the graph of f at x equals c. It's also the same as finding the instantaneous slope of the graph of f at x equals c. Okay, or also the instantaneous rate of change. All of these things are synonymous. Instantaneous. Sorry, I have to sound it out. That's how I was taught way back in elementary school about how to spell things. Sound it out. Okay. So all of these things are synonyms. Synonyms. They're synonyms, okay? So there you go. Slope of the tangent line, slope of the graph of f, instantaneous slope, instantaneous rate of change. That's all the derivative, the slope of the tangent line, using that f of x plus delta, or limit x, delta x approaches 0 of f of c plus delta x minus f of c all over delta x, okay? So, we will pause there because I'm sure they're going to call you guys, but doggone it, we're just going to get to our first problem. Oh, so sad.